Okay, AP Calculus AB, Unit 5, Day 7. This is our last lesson of Unit 5. We got a few more assignments just to help you get ready for the test. But first off, here you go. Here's a warm-up problem. Should really take you 5 minutes or less. It's a function table problem, so you know you're gonna, or you should expect to get some problems like that on your next test. So pause the video, try the problems, and then we'll go over them. Okay, so when you try the problems, I would say, well, we got to do G1, which is 4, F4, which is 0. Done. So I do want to see work on these. Now we want P prime, so you should do P prime first. So that'd be G prime minus F prime. You can take derivatives of each term separately, that's fine. So then we plug 2 in. And then we look up these values. G prime of 2 is 4. F prime of 2 is 3. So the answer is 1. Next one is a little chain rule. Q prime. Derive the outer function first. Leave the inside the same. Times derive what's inside. That's the chain rule. So then we're going to do Q prime of 2. So we'll plug 2 into everything. And so G of 2 is 1. And F prime of 1 is 2. And G prime of 2 is 4. And so the answer is 8. Share your work. It'll help you make less little mistakes. It'll help you get partial credit when you do make mistakes. Now here's something a little more new. Find the x-coordinate of all horizontal tangents. It sounds like a question we've asked about horizontal tangents. The slope equals 0, right? So we got to take the derivative of the function, which has a little chain rule in it. Got to take derivative of the function times derivative of what's inside, and then we're going to set it equal to 0, right? So now zero product property, which we use all the time, says that G prime of f of x has to somehow give you 0, or f prime of x has to give you 0. So these are going to give you multiple answers. What would you plug into f prime to get 0? When does f prime equals 0? When x equals 3. Okay, how about over here? What would you plug into here? What would you plug in G prime, where the fx is, to get 0? Well, you plug 1 in, so that means fx equals 1. And then you say, well, what do you plug into f? What value of x do you plug into f to get 1? 3. Now, that's just coincidence that we get the same root twice. It's like a double root. But usually those are going to give you two separate answers. For your final answer, you're just gonna write it once. I don't need to write the answer twice. But just watch out. You might get two answers, and if you didn't show me this work, I would take out points anyways. Okay, so that's kind of like a question we've asked before, but never like in this kind of context. Find the equation of a tangent line. Hey, that's a classic question when we need two things. You need a point and a slope. So y value is going to be whatever g of 4 is, which is 2. So your point is 4 comma 2, right? We need the slope. So that'd be y prime, which would equal g prime. So y prime of 4 equals g prime of 4, and g prime of 4 equals 1. That's your slope. So the equation of the tangent line is going to be y minus 2 equals 1 times x minus 4. Now we just leave it like that. If you really like doing more work, go ahead. But just know, if you make a mistake, you're losing points that you could have had full credit for. So there you go. So that was a good little warm-up problem. You're going to have some problems like this on your next test. Now, just a little more practice with implicit differentiation. So, I don't know, just some problems that maybe we could try and look at some creative ways to do it. Find the slope of the tangent line. How can we make it easier? So, the way it is right now, we could do it, but it would be pretty messy. We could do x times 2y first, dy dx. plus y squared times derivative of x is 1 plus 3y squared dy dx equals 3 dy dx. Now we're looking for the slope of the tangent line, so just the slope, which is dy dx, which is all over the place here. But we've been given a very specific term, so I wouldn't try and get dy dx by itself. That's a lot of extra work for nothing. I'd be plugging these numbers in right now. 2 in for x, 1 in for y, 1 in for y, 1 in for y. And this is going to make it a little easier. So it's going to be 5 dy dx plus 1 plus 3 dy dx equals dy dx. And then we get all the dy dx's together. So there's 8 minus 1 is 7 dy dx's, and we move the 1 to the other side, and then we just divide by 7. So we get negative 1/7 for the slope. Now, let's see, did I do that all correctly? Let me make sure. I feel like I might have made a mistake. That looks good. Oh, shoot, I lost this 3 right here. So that really should have been 8 minus 3. Or this should have been 3. This should be 8 minus 3 is 5. Does that make sense? Let's see. Oh, this should be a 4. Gosh, man, I'm making lots of mistakes. 7 minus 3 is 4. So it should be 1/4. Now, an interesting alternative way of doing this problem is maybe we could simplify it. Like, could we divide a y out of everything? Well, I don't know. Let's try it. I don't know. And we'll see if it makes it that much easier. If you divide a y out of everything, you get this. And take a derivative of it. Implicitly, x times derivative of y is dy dx plus y times derivative of x is 1 plus 2y the first dy dx equals 0. So yeah, it's a little simpler. And then we plug in the x, y pair. So we plug in 2 for x, 1 for y, 1 for y. So we have 4 dy dx. Subtract the 1 on the other side. Dy dx equals negative 1/4. Sure. So I guess, that was kind of an interesting maybe idea. But since this is a numerical, since we're looking for a numerical answer, meaning a number, just plug x equals 2, y equals 1 in before solving for dy dx, which is something I was trying to explain yesterday too. So that, I think, makes it easier. That's the way I did it both ways. Okay. Let's look at the next page. So, I mean, this isn't even so much another lesson as just some more examples. I am going to do second derivative with implicitly, which we haven't done yet, and that gets a little messy. So now let's try this 2 different ways. Let's try it the way it's written, like this. So it would be 2x equals low d high 1 plus dy dx, low d high, minus high d low 1 minus dy dx, all over low squared. I mean, it's pretty messy. We're going to solve for dy dx. I would multiply both sides by x minus y squared to get rid of the denominator. So then 2x, x minus y squared. And over here, I'd probably go and distribute this. So it's going to be x minus y plus x dy dx minus y dy dx minus x minus y plus x dy dx plus y dy dx, because the negative gets distributed and then there's another negative there which makes it positive all over nothing. We got rid of the denominator. Okay, negative y dy dx and positive dy dx cancel. We want to move everything on one side. I think it might be worth it to go ahead and multiply this out. This is going to be 2x times x squared minus 2xy plus y squared. And then we're going to, x and negative x cancel each other out. There's a minus 2y, so it becomes plus 2y over here. And then we have 2x dy dx's. So dy dx equals 2x cubed minus 4x squared y plus 2xy squared plus 2y all over 2x. And we could definitely reduce at least a 2 out of everything. So then that would be x cubed minus 2x squared y plus xy squared plus y over x. So there's our answer. That's just doing it the regular old normal way. Okay. Alternatively, let's see if this works. Let's cross multiply first, because that quotient rule is kind of nasty, right? So what if we cross multiply first? Let's try this. So you would get a x cubed minus x squared y equals x plus y, right? Let's try that derivative, which I think is going to be potentially a little cleaner than this one. This one was kind of messy, but let's see. It's going to be a 3x squared minus. Now be careful. There's a product rule here that you have to subtract the whole thing for. So you either include the negative as part of one of the terms or put it outside parentheses. So x squared dy dx plus y times derivative of x squared is 2x equals derivative of x is 1, derivative of y is dy dx. Now that derivative seemed a little easier. Now let's try and solve for dy dx. So we want to distribute that. 3x squared minus x squared dy dx minus 2xy equals 1 plus dy dx. So we want to get the dy dx's on the same side and the non-dy dx's on the same side. I'm going to move the 1 over here and the dy dx term to the other side. Now there's already a 1 dy dx, and then now there's going to be a plus x squared dy dx, and I'm going to factor. Okay, so then we're going to get dy dx equals 3x squared minus 2xy minus 1 over 1 plus x squared. That's our answer. Now, do these look exactly the same? No, they don't. But are they equivalent? We could maybe try some value, like try x equals 1, but we need a y value to go with it, so we would plug that in up here. So this is just illustrating. If they give you an x and you're like, well, but what's the y? Well, plug it in up here, just like you've been doing since algebra 1 to find the y value. If you have an x, you can find a y. If you have a y, you can find an x. So then this would be 1 minus y equals 1 plus y. And then this would be 0 equals 2y, and y equals 0. So if we plugged x1, y0 into both of these, hopefully that means that this point is on both functions, which it needs to be to check this. And then it should give the same slope, hopefully. You can't just plug any xy parent because it might not be on one or both of the functions. So it might not make sense. So if you do this one, you get 3 minus 0 minus 1 over 1 plus 1 is 3, 2 over 2, which is 1. If we do this other one over here, we get 1 minus 0 plus 0 plus 0 over 1, and we get 1 that way too. So, I don't know. I actually am a little sketchy about this, dividing that y out. But at least the point we checked worked. If we really wanted to feel better about it, we could check another point. And if that one worked too, that's pretty amazing that if it's just an accident. Now, here's an interesting new challenge. How do we do second derivative implicitly? Because we've been doing second derivatives before, and that's just the derivative of the first derivative. So you have to do, let's do the first derivative implicitly. So x times 3y squared dy dx plus y cubed times derivative of x is 1. So that's that product rule right there. Plus derivative of x is 1 equals derivative of 1 is 0. Now, what we would want to do here is go ahead and get dy dx by itself before you take. You could take the second derivative now, but you're going to have to get dy dx by itself probably for some reason I haven't showed you yet. And it's going to make the second derivative easier if you do that. So we're going to go ahead and do that. So we're going to say, okay, well, it's 3xy squared equals negative 1 minus y cubed. I forgot the dy dx. And then so dy dx equals negative 1 minus y cubed over 3xy squared. So that's the first derivative implicitly. So now the second derivative says, okay, take the derivative of this. So we're going to take the derivative of this, and we're going to do a quotient rule. And it has y's in it still, right? So it's going to be low d high, which would be negative 3y squared dy dx. Low d high minus low d high minus high d low. Now d low is going to have a product 3x times derivative of y squared would be 2y dy dx plus y squared times derivative of 3x would be 3 all over low squared. Oh my gosh, that's messy. Now, usually we're okay with x's and y's in our derivative answers for implicit, but we don't want dy dx's in our second derivatives, okay? So what do we do with these guys? It's actually not that hard. Right here, look. You just found dy dx on the previous step. So we're going to it's ugly and terribly messy, but it's kind of simple. We're just going to substitute this in for those. So now we just have purely x's and y's. So let's see what we get. It's going to get interesting. So we could do some other clean housekeeping too. Negative 9xy to the fourth, and then negative 1 minus y cubed over 3xy squared. And then this is going to be plus 1 plus y cubed. Now distribute that negative into that just to make things a little nicer. 6xy negative 1 minus y cubed over 3xy squared plus 3y squared all over 9x squared y to the fourth. So we got rid of all the dy dx's, but now we have complex fractions and it's pretty ugly. So let's see if we can clean this up even more. I mean, this is kind of gross. Now, what I would do is multiply the top and bottom by 3xy squared. That's the way to get rid of complex fractions. So if we did that, it gets distributed to everything. So it gets distributed here, and those cancel each other out. So you get positive 9xy to the fourth plus 9xy to the seventh. Now when you distribute it here, it cancels out for this first term. And so you get all this stuff right here. So we're going to get, wow. I mean, it's going to become 6xy or negative 6xy minus 6xy to the fourth. But then this guy gets the 3xy squared. So it's going to be 9xy to the fourth. And then we got to FOIL this stuff out. So it's going to be minus 6xy minus 6xy to the fourth plus 9xy to the fourth. And then we're going to distribute a y cubed. So it's going to be minus 6xy to the fourth minus 6xy to the seventh plus 9xy to the seventh. And on the bottom, we get 27x cubed y to the sixth. Oh my gosh. All right, can we clean this up anymore? Any like terms? I mean, so for instance, xy to the fourth, xy to the fourth, xy to the fourth, xy to the fourth. There's a bunch of xy to the fourths. And so 9 plus 9 is 18, minus 12 is 6 xy to the fourth. And then xy to the seventh, there's an xy to the seventh, xy to the seventh, xy to the seventh. So that's going to be 18 minus 6 is 12 plus 12xy to the seventh. And what's left is a negative 6xy. And then can we reduce anything? Take a 3 out, right? Of everything on the top and bottom. We could take an x out of everything on the top and the bottom. We could take a y out of everything on the top and the bottom. So what's left? Oh, these guys cancel each other out, by the way. 2 and the minus 2, they go away. So now, well, no, they don't. Sorry, they still got some stuff. This still has a y cubed. So we have a 2y cubed plus 4y to the sixth minus 2 over 9x squared y to the fifth. That's probably our best answer for the second derivative. Now, I'm not going to give you problems this crazy. I'm not going to make you do this, but it was definitely good practice. But that's the idea, okay? So you got to take the first derivative, solve for dy dx, then take the second derivative implicitly, replace the dy dx's with the dy dx you found halfway in your work. Here's homework. Mostly odds, all but one odd. So check your answers in the back of the book. I guess I could go ahead and give you the answer to 14 right now if you want. You got to do the work. This is what I got for 14. Let's see, 14. I got negative 1 plus 10xy minus 3x squared y squared over 2x cubed y minus 5x squared. That's a nice answer. Anyways, try those. Check in the back of your book. And this was our last lesson for Unit 5. So we're gonna have a few more assignments to get really good at this stuff. This test is all about details, knowing a handful of rules and executing them correctly. And there's a lot of room for little mistakes. So show your work and be careful, be organized.